In this tutorial, I'm going to focus on the Taylor-Green Vortex case, which is one of the most well-known benchmark in CFD. So once you have installed and compiled the latest master branch of Xcompact3d, you can go in the examples directory and pick the Taylor-Green Vortex case. For this tutorial, we are going to focus on the input DNS Reynolds 1600. Which I'm going to use here, and I'm going to start the simulation with 16 cores. And while the simulation is running, I will go through the input file and some information about the post-processing. So the simulation should, on a modern workstation, should run in 5-6 minutes, no more than that. So if we look at the input parameters, we can see that the Reynolds number is 1600. You will notice that the boundary condition, the domain is only pi cube and not the usual 2 pi cube, simply because we are using the symmetry of the flow, and basically you can switch from a 2 pi cube periodic domain to a pi cube free slip domain. So here we are using NCL equal 1, corresponding to free slip boundary conditions in the 3 spatial direction, and a computational domain of pi cube with mesh of 65 cube as well. I will show you just after that you can run a similar simulation if you are more comfortable with a 2 pi cube periodic box. We can do that very easily, and I will show you the parameter to change. The time step is here, dt equals 0.005. We are using the classic 6-order schemes for the first and for the second derivative here, and we are using Runge-Kutta 3 explicit time advancement. Another parameter of interest for you is the frequency at which you are saving the snapshots. So here we are doing 4000 time step. We are saving snapshots every 1000, so we are going to produce 4 snapshots. In terms of snapshots, by default, Xcompact3d will save U, V, W, and P, but for the Taylor-Green case, we have added the calculation of the vorticity and Q criteria. So I will just show you where to look out for. So we go in the BC specific file for the Taylor-Green, and we look at first the Visu TGV, which is any extra snapshot that you want to compute during the simulation. So here we have the vorticity field, and here we have the Q criterion. Here, this is the calculation of the 9 velocity gradient in X, Y, and Z direction. So this is a good example if you want to play around and compute your own quantity of interest. You can be inspired by the calculation of the vorticity and the Q criterion. The other subroutine of interest is the post-processing one, and for the Taylor-Green case, it is customary to compute spatial average of various quantity like the energy dissipation, the entropy, or the TKE. And once again, this subroutine is a good example on how you can do your post-processing on the fly. So here, once again, this is how we compute the 9 velocity gradients. Then we can compute the entropy and the dissipation. And you can also compute the second derivatives as well, and compute the dissipation with the second derivative formula. So this is, if you want to make some changes in your post-processing, this is where you will have to play around, and the Taylor-Green case is a good example on how to do that. So we are going to check that the simulation is still running fine, which is great. So in the meantime, I'm going to prepare a new input file. So I'm going to call it input periodic, just to show you how you will switch from free slip boundary condition to a periodic boundary condition. So first we need to change the boundary condition. So here we switch from 1 to 0. 0 corresponding to periodic boundary condition, 1 corresponding to free sleep. We need a computational domain of 2 pi. So here for simplicity, I'm just going to use 2.28 as an approximation of 2 pi. Of course, if you want to run your simulation perfectly, you will have to put the value of 2 pi up to 14 digits in double precision. And here, to have an equivalent simulation, we need to change the resolution to 128. So why 128 and not 129? This has to do with the fast Fourier transform. When you are using periodic boundary condition, you have one less point, and the resolution should correspond to a combination of power of 2, 3, 5, 7, 11, 13, so prime numbers. And when you are using different boundary conditions like free sleep, you just need to add a +1 at the end. You have an extra point in your computational domain, as the boundary conditions are not periodic. So here I've changed the mesh size, I've changed the domain size, I've changed the boundary condition. So here it means that with this new input file, I will be able to run the exact same simulation. Of course, it's going to cost me 8 times more because the resolution has been increased, but in principle, I will get very similar result to the simulation that I am currently running. Right, so the simulation is finished. Took a little bit more than 5 minutes. So the next thing I want to have some comparison with some reference data. So I suggest you go on the ukturbulence.co.uk website. There is a database section where you can find the Taylor Green Vortex DNS statistics from Reynolds 1350 to Reynolds 20,000. You have a lot of data. We are going to focus on the kinetic energy and the dissipation. And for the comparison, so I'm just going to download this 1600 case. Here it is. I am going to put it in my directory. Sorry. And then I'm just going to use GNUplot to look at what the data are with the reference data obtained by DNS at high resolution, of course. And you can see that there is a fairly good agreement with my very low coarse, poorly resolved simulation. I'm just going to look at the third column as well. And you can see that we have a fairly good agreement with that. So this is for the statistics. If we look at the snapshot, so the snapshots are going to be located in the data directory, and we are interested in the XDMF file. Okay. So let me just check what I have done here. So as I said, we have generated 4 snapshots. So I'm using PowerView to do the visualization. It's PowerView friendly, and I'm just going to load. I'm going to go in the data directory. Sorry, it's a bit slow sometimes, and I'm just going to load the first 4 snapshots. The other ones are not relevant. We need to use the XDMF reader. Okay. So I'm just going to look at the data with, I'm going to use the Q criterion, it's a good one. I'm going to use a value of 1. And you can see you have a nice, going to do the coloring. So I'm using the rainbow desaturated color code, and you can see you have a fully turbulent state. So that's quite nice. So this is how you will we can look at the instantaneous. So that would be the first how the Q criterion look like after 1000 time step, this is how it will look like, right? So you go from here to here. Basically, as you can see, within 5 minutes you can get a nice fully turbulent Taylor Green Vortex case running, and you can do the visualization very easily with ParaView. The one last thing I want to do, I'm now going to switch to just to show you, we have this input periodic. I'm going to load it. I'm not going to run the full simulation because it's going to take quite some time, but just to show you, it's probably going to take about an hour or so, a little bit less than an hour. So yeah, it's going to go down to under an hour very quickly. But then you can run the 3 periodic box on a 2 pi cube domain. Okay, and just to show you that the data are consistent. So I've run this simulation before. I saved the data. Right, so I have the time evolution for a periodic box for this resolution, and I'm just going to show you on GNU plot that you get very similar results to the simulation with free slip boundary condition. Here you are. So you can see that you also get a good agreement. So because I've started the new simulation and I didn't save the old time evolution, there is no green plot, but you can see that the periodic simulation will give similar results. If you want to increase the resolution, then you can, and then you will match eventually the reference DNS data. So the Taylor Green case is a nice case to get used to run simulation of turbulent flow with Xcompact3d. You can see that you can very easily visualize the snapshot with ParaView. There is no post-processing needed. And you can also look at relevant statistics very easily using MATLAB, Python, or GNU plot.